In section 7.2, we're going to learn about another way to measure consistency or variability, and that's through using the standard deviation. This is probably the most common way that we measure variability in statistics, and one that we will see used throughout the rest of this course. When we calculated the mean absolute deviation in the last section, we took the absolute value of each deviation to make sure that the deviations don't have a sum of zero. Another way to eliminate negative deviations is to square them. And this leads us to our next measure of consistency or variability, which is called the standard deviation. Now, the standard deviation measures the variability in a distribution using the squared deviations from the means. This is a measure of the typical distance between an athlete's performance and his or her true ability. Now, the formula for the standard deviation is given here. So what we do is we take each performance, X, minus the mean performance, which is X bar in that formula, and then we square it, and that eliminates the negative signs. Now, what we want to do then is we want to add up all those squared differences. We're going to then divide that by n minus 1, where n is the number of performances the athlete has. And then what we're going to do is take the square root of that quotient, and the square root kind of undoes all the squares that we did earlier in the problem. Now, you may be wondering why we divide by n minus 1 instead of n, and that's kind of a complicated explanation, which if you go on to take AP statistics, you'll sort of learn why we do n minus 1 instead of n. For now, you don't need to concern yourself with why. Just know that n is the number of performances in your data list. We're going to do a calculation for standard deviation by hand with a very small data set, just so you can kind of become a little bit more familiar with the formula. And we're going to look at a very small data set of 4 values where Paul has bowled in 4 tournaments, and we have his bowling scores listed there. And we want to use the formula to calculate his standard deviation. So the first thing we have to do is we have to calculate his mean bowling score. So if I add those 4 scores together and divide by 4, I get a mean of 224 points. So now in the little chart, we're going to fill in the columns. And the first column there in the middle that you're going to fill in is each performance minus the mean. So if I do 211 minus the mean score of 224, I get a difference of negative 13. The second one, we have a positive 1 difference. Then we have negative 26, positive 38. Just like we did in the last section, some of those deviations are negative, some are positive. Notice that if you added those together, you would get a difference, or a total sum of 0 rather. Negative 13 plus 1 plus negative 26 plus 38 is in fact 0. Now, to eliminate those positives and negatives, what we want to do is square each of those differences. So negative 13 squared is 169. 1 squared is 1, negative 26 squared is 676, and 38 squared is 1444. Remember that when you square negative numbers, you end up with a positive, because a negative times a negative is a positive. Now the formula says to sum all of those squared differences. So if I add up all the numbers in that last column, I get a total sum of 2,290. The next thing the formula tells us to do is to divide by n minus 1. And in this problem, n is 4 because Paul has 4 bowling scores. So we're going to take that 2290 and we're going to divide that by 4 minus 1. Or in other words, I'm going to divide that by 3. I'm going to leave that as 4 minus 1. So later on, when I go back and look at the work, I remember why I used 3 there. And then the last thing you're going to do is take the square root. Now, what I would recommend that you do is divide 2290 by 3, keep that number in your calculator, and then take the square root of that answer. What you don't want to do is round off at that division step and then take the square root. You want to save all of your rounding for the very last step, because that's going to make your answer more precise. And if you do that and then round, you'll get a standard deviation of 27.6 if we round that to 1 decimal place. All right, so the formula is not super complicated, but you can imagine that if you had a large data set, it would be very time consuming to do this by hand. So we're also going to show you how to do this on the calculator. First, let's interpret the standard deviation though. We would say Paul's performances in the tournament typically vary from his ability by 27.6 points. Now, notice this is a little bit different than how we interpreted the mean absolute deviation, which was how much the performances typically vary from their average performance. Here, we're looking at how much they typically vary from his ability. All right, let's take a look at example 2. And in this one, we're going to use the calculator to do the standard deviation. We have the number of passing yards from Kurt Warner of the Arizona Cardinals in each of the 16 games that he played in the 2008 NFL regular season. So these are in order by the games that he played, not by smallest to largest or anything like that. So we're going to use the calculator to find the mean and the standard deviation. Now, what I would do is I would put those 16 games into list one in my calculator and then use the one variable stats function to do the mean. And you already are familiar with how to do that. This is what your calculator display will look like when you do the one variable stats function. So you'll notice X bar at the top is your mean, right? We've used that in the past. We know that if we scroll down, we could see the median and Q1 and Q3 and so on. The other value that we're going to look at though today is the standard deviation. And the standard deviation is right here. That's the S of X. And notice that in this case, that's about 103.24, and our mean is 286.4375. Just to make things easier for this problem, we're going to round those off to whole numbers. Typically, we won't do that, but in this one, just to keep it a little bit simpler, we're going to round those to whole numbers. But the one variable stats function will do the standard deviation for you just the same way that you would do the mean and everything else. There's no difference in this key sequence that you would need to push. So let's say the mean in this case is 286. Remember, we use X bar as the symbol for the mean. Standard deviation is 103. How we would interpret that standard deviation is to say that Warner's performances in the 2008 season typically vary from his ability by 103 yards. That's a pretty big standard deviation there. In case you're wondering why the standard deviation is so large, we've got one game, notice here, where he only had 30 yards. And that very small number, which is quite a ways away from the rest of his games, is what's responsible for making the standard deviation so large. Now, question C asks what percent of his performances were within one standard deviation of the mean? And they give you a hint here to use your calculator to sort the data and then list them in order. So I'm going to do that here. I'm going to just put all those games in order with the smallest number of yards first up to the largest number of yards. And we want to know what percent of his performances were within one standard deviation of the mean. Now, remember, the mean was 286, which is right about there. And that's not quite in the middle of the data. And that's okay. And that's because of the way that the data is sort of distributed there. Within one standard deviation means from one standard deviation below the mean up to one standard deviation above. So if we do the mean minus one standard deviation, or 286 minus 103, that would put us at 183 yards. The mean plus one standard deviation would be 286 plus 103, which would put us at 389 yards. So if we go back and look at all of his performances, almost all of them were within that range from 183 up to 389. In fact, we had 13 of his 16 games, or 81.3%, within that range, which is most of the games that he was in. Now, in example number 3, let's suppose that we want to compare the consistency of two brands of golf balls, one cheap and one expensive brand. We want to be able to predict how far the ball will travel when hit with as much precision as possible. Golf is really a game of precision, and so you are probably better off being able to hit the ball consistently and know that approximately how far it's going to go with each hit, rather than have some that go really far and some that don't go as far. So, to conduct an experiment, you take an experienced golfer and they hit 10 golf balls of each brand in random order using the same club, and we have the results shown in the dot plot. Part A is asking us to estimate the mean of each type of golf ball. So, the mean would be about in the middle. This data is pretty uniformly distributed or symmetric, so we can kind of estimate where the middle would be. I would say for the cheap golf ball, the mean is probably right about there. We would estimate that that's maybe 192, 193. For the expensive golf ball, the middle is a little bit higher. That's would say maybe at about 202. So with the expensive golf balls, we can probably hit them a little bit further on average. But which one would have the largest standard deviation? Well, without having the data, we can't really calculate it, but we can estimate from looking at the dot plot just by determining which data is more spread out. And we can see pretty clearly that the cheap golf ball is going to be a little bit more spread out than the expensive golf ball. So it's going to have the larger standard deviation. The data is more spread out from the mean. And part C says for the distribution of expensive golf balls, is the standard deviation going to be closest to 1, 5, or 10? So I have an arrow there again, kind of marking where the middle is. And we want to kind of look at what is a typical distance from the mean. So one way that I would do that is I would maybe look at from here to here, right? How much deviation actually is occurring? And this is from about 202 to about 212, which is about 10 maybe. And so if we kind of cut that in half and we say that that's about the typical distance or the average distance, that would give us a deviation of about 5. So we can say in this case that our standard deviation is probably going to be closest to 5 because that's a typical distance from the mean. It's not the biggest, it's not the smallest, it's kind of right in between. Now, part D says suppose that the golfer hit one more expensive golf ball and it only traveled 177 yards. What effect would this have on the mean and also on the standard deviation? So, 177 is way down there, right? That's quite a bit shorter than the distance that he had been hitting the expensive golf balls. When we throw in that one value that's a lot lower than the rest, what that's going to do is it's going to bring down the average distance, right? Because we're adding in a very low value compared to the rest. Think about if you have a good grade in a class and you typically get A's and B's on your tests, and then all of a sudden you take a test and you get an F, that F is going to bring down your average grade. And the same thing is going to happen here. So that one value there is going to decrease our mean. Now, on the other hand, when we talk about how the standard deviation is going to change, now you have this data point that is very far from the mean. And so, what that's going to do then is it's going to increase your standard deviation because this performance minus the mean is going to be a large value that then is going to get squared and calculated into that formula. So, our standard deviation in this case would actually increase. Please do homework 7.2 in your assignment packet.